Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. In that we are discussing the process integration, and today we are starting with the well formation. So in the history of the IC fabrication, I told you we started with the PMOS type of IC chips and then we moved on towards the NMOS chips, and now after that we started manufacturing the CMOS chips, which were faster than both PMOS and the NMOS chips. So CMOS chips, because of its various advantages, was more popular than PMOS as well as NMOS chips. So now we should know what is the basic structure of the CMOS. I hope you know the basic structure of the CMOS. I have already talked about it as well in the previous video. In the unit 1 I had talked about its structure. So in the structure I told you there is a well that is formed for the formation of the CMOS structure. Now we can have N type of well or the P type of well, or both N well as well as P well in the CMOS structure. Right, so based upon the type of well that we are using, we can classify the well formation into 3 types, that is the single well process, the self-aligned twin well process, in that we have 2 wells, and then we have double photo twin well process. So all of them completely makes the well formation, and after that we can proceed with the various ion implantation diffusion technique and the various further techniques for the chip formation. So we should understand how we are forming the well, and for that we are moving towards the single well process, which was the earliest process for the well formation. So the early CMOS IC processing was based upon the single well process. There I was using only 1 well. So when I had the P type wafer, I was using the N well, and when I had the N type wafer, I was using the P well. So only 1 well was required in the single well process. For that I was using high energy, the low current ion implantation process. So when I was using high energy ion implantation process, high energy ion particles are bombarded on the surface. So when high energy ions are bombarded on the surface atoms may get degraded and the single crystal structure would be degraded. I want it back. For that I will be using the thermal anneal and the drive-in process. In the drive-in process we are giving high temperature so that the ions will penetrate deeper inside the substrate. So I hope you understood the single well process. So this is the pictorial representation. First of all, we are going to clean the wafer so that there would not be any contaminant particles on the wafer. After that we are going to have a screen oxide layer. So we have a very thin screen oxide layer over the wafer, and after that we are going to form a mask with the help of the photoresist, right? So with the help of photolithography, with the help of alignment exposure process in the photolithography, we are going to make a mask. I hope you remember the photolithography process. And with the help of high energy phosphorus ions in the ion implantation process, we are going to form the N well over here. So this is the ion implantation process. After that we have the photoresist strip. We don't want this photoresist after this step, so we are going to strip the photoresist after this, and after that we are going to have the annealing and drive-in. So in the drive-in we are going to give high temperature, also in annealing we are going to give high temperature, so the depth of this N well is going to increase, and after that we are going to remove the screen oxide. So this is the third and the last figure which represents the removal of the screen oxide. So here you can see we are having a P-type silicon, over that we are having the N well. So this is how we can form the single well or the N well. So you can see the structure of the CMOS with the P well. So in the similar manner I can form the P well as well. In the N type of silicon we have P well, in which I can dope N plus regions, or here in the N type structure we can dope P plus region, and this is how we can form the CMOS. We will be having a polysilicon layer over that, and we will be having the field oxide layer, which can be used for the metallization, shortening, removal. So after this process we are going to form a metallization layer with the help of aluminium silicon or aluminium silicon copper alloy. So you can see here after metallization, so that this structure and this structure will not get shorted out, I am using this field oxide layer, right? The polysilicon is having its resistivity in between the metal and the isolators. So this is how polysilicon is used, because of its various advantages that it provides over the metals, right? So this is the gate we have. So now this is a CMOS with the N-well. So in the CMOS with N-well, we are using the P type of substrate over here. In the P type of substrate, this is the additional thing we have, that is the isolation implantation, so that this structure will not be shorted out, right? So here we are using the polysilicon gate and the low-cost silicon dioxide for the isolation implantation, right? So now here SiO2 layer is going to isolate this MOSFET and this MOSFET. So this is having N type of source and drain, and here we have P type of source and drain. So here we will be having the gate oxide, and now this gate oxide is having a polysilicon gate layer over it, like in the previous case we had. So this is the CMOS structure with the N-well. Now coming to the self-aligned twin well process. In the self-aligned twin well process, we are having the two wells. It is going to give more flexibility to the designers, right? So it is going to give more flexibility to the designers, and plus we are going to save a masking step as well. So both of them are the advantages. So the self-aligned twin well process is a better process than the single well process. Here we are forming the gate with the polysilicon. Now when we are forming the gate, now we have to align this gate in between the source and drain, right? So here we have source, we have drain. The gate should be aligned at a proper location. If it is displaced towards the source or towards the drain, then some errors might occur. So I have to save these errors, and for saving these errors I can use the self-aligned twin well process. Here the alignment issue is not there. So here I am using the LPCVD of the silicon nitride, which is a very dense layer of the silicon nitride. So it is going to block the ion implantation on the P well as well. So I don't require the photoresist layer while the ion implantation process. So I can remove the photoresist layer, I can just keep the silicon nitride layer, and then I can do the ion implantation, so that the contaminant particles which are coming from the photoresist will be avoided in this scenario. So it is going to prevent the oxidation on the P well as well, because I have removed the photoresist layer. After that, the oxide grown on the N well, it is going to block the P well ion implantation. So this is how I will be having saving of a masking step. So this is how all of the steps are looking like. So first of all, we are going to clean the wafer. After that, we are going to have a pad oxide layer. After that, we are going to have the nitride layer. We are growing the pad oxide layer below the nitride layer, so that there would not be a pressure that is encountered on the silicon with the help of the denser nitride layer, right? So first of all, we have deposited the nitride over the pad oxide layer. This is represented in this diagram. After that, we are going to make the N-well mask. Here with the help of photolithography process, I had made the mask, and then I will etch the nitride, right? So you can see we have etched the nitride over this part, and after that we are going to strip the photoresist that is present over the nitride layer, and after that I am going to do the ion implantation. So here I am doing the N-well ion implantation. This is represented in this diagram. After that, we are going to give the annealing and the drive-in phase, and in the annealing and the drive-in phase we will be having the oxidation also. So here you can see we have an extra layer of SiO2 deposited. It is going to protect our layer for the next ion implantation. So now we can remove the nitride layer, and I can do the boron ion implantation for the P-well formation. So after that we can remove the silicon dioxide, and I will be having N-well as well as P-well. Right, so you can see after annealing, drive-in and the oxidation, we are going to strip off the nitride from this part, and after stripping it, we are going to have the P-well implantation. So this is how we have saved a step. After that, we are going to have annealing and drive-in, so that N-well and P-well will be single crystal, and it is going to have a greater depth. And after that, we are going to strip the pad oxide, so that we will be getting E type of layer. This is the twin well structure that we have. So now the advantage, so it is going to reduce a photo mask step, that is going to reduce the cost. Obviously, if I am going to reduce any step, it is going to reduce the cost, it is going to reduce the time as well. So it is going to improve the IC chip yield as well, because with the help of every step or every masking process, I might be exposed towards the errors also. So if I have lesser number of steps, the possibility of error would be less, and this is how I can improve the IC chip yield as well. Now coming to the disadvantage. The disadvantage is that the wafer structure is not flat. You can see here the N well is somewhat deeper than the P well. Okay, so this is how I don't have a flat wafer surface. So this is the only disadvantage. So now N well is always having a lower level than the P well surface. It is going to affect the photolithography resolution in the next steps, and it is going to affect the thin film deposition as well. After steps would be complicated because here I am not having a symmetric structure, I am having unsymmetric structure, and for that the next step would be complicated. So first of all I am going to implant the N well, because the phosphorus diffuses slower than the boron in the single silicon, and if I am going to implant the P well first, then the boron in the P well could diffuse out of the control during N well annealing and drive-in. Because for the boron I might not require that much time and that much temperature, but for phosphorus diffusion I require larger time and larger temperature. So this is the reason we are going to implant the N well first. Now coming to the twin well process. In the twin well, as I told you, we have the two mask steps. We are having the flat surface now. It is commonly used in the advanced CMOS IC chips. Here I will be using the high energy and the low current implanters. After that we will be using the furnace annealing and the drive-in. So you can see in the twin well process I will be having two masks. So here we will be using the one mask for the N well, and this is the second mask for the P well. So here I am not saving a masking layer. So this is the difference between self-aligned twin well process and the twin well process. So I hope you understood each one of them in detail. If you have any doubt, you can put the doubt in the comment. Further, you can refer these books. These are really amazing books. If you want to connect with me, you can connect with me with any social media site as well. If you like this video, please push the like button, subscribe to the channel, give me your feedback, share it with your friends. Thank you so much.